Hi, folks. Want to welcome you to the How to Better Manage Your Fog-Related Wastes webinar. We'll give everyone maybe one more minute to try to join us. So give us a minute. All right, folks. I want to welcome all of you to this webinar titled How to Better Manage Your Fog-Related Wastes. My name is Ed Gonzalez. I am the director of PPRC, and we are a Seattle-based nonprofit organization established in 1991. We were established to provide outreach and to develop P2 content and provide on-site technical assistance and training to businesses in Alaska, Idaho, Oregon, and Washington. So welcome to the webinar, folks. Today's webinar is brought to you by the Western States Alliance, a membership organization of wastewater and pretreatment professionals in the Pacific Northwest. The Western States Alliance is a program administered by PPRC, and this webinar is made possible through support from the USDA's Rural Development Office. So the purpose of this webinar is how to improve your fog abatement program by properly evaluating grease interceptors. And some of the topics that we're going to be addressing is what types of grease interceptors are available, what are the differences between grease interceptors, and how do you select the correct grease interceptor for your needs? How are grease interceptors tested? But before we start, I would like to do some housekeeping rules here. A recording of this webinar will be made available on PPRC's YouTube website. The page is, you see it right there on the screen. It'll be made available sometime within the next 2 weeks, and I will send out a notice to everyone on this webinar, letting them know when it's available. The conference line is muted, and the questions will be addressed at the end of the webinar. And submit your questions using the question window or bar on your control panel. And after the conclusion of the webinar, within a week, a short survey will be sent to you regarding the webinar. So please fill it out and when you receive it and send it back. We have two speakers today, two experts in fog abatement. And it's Ken Laux and Clayton Brown. Ken has extensive experience and is an expert in dealing with commercial grease interceptors. He knows how they work, the codes and standards that govern them, and the stakeholders affected by them. Ken is a member of many organizations, such as the American Society of Plumbing Engineers, the American Society of Mechanical Engineers, and the California Water Environment Association, and the Western States Alliance. Clayton Brown is an award-winning clean water industry professional with over 21 years of pollution control and water treatment experience. He helped start the Regional Preferred Pumper Program in Oregon, which is a budding green certification program. For 30 years, Clayton was a source control manager at Oregon's Clean Water Services, a water resources management utility. Clayton's current role is board chair for the Pacific Northwest Source Control Training Association and is the current WSA program manager here at PPRC. Now, folks, it's time to pass the controls to both Ken and Clayton.
Thank you, Ed. Ken, say hello.
Good afternoon.
As Ed mentioned, this webinar is brought to you through a Department of Agriculture Technical Assistance grant. It's also provided grant money for us to do one-day workshops, which we've done across Oregon, Washington, Idaho, Alaska, Montana, North and South Dakota, and Colorado. So it's pretty exciting. We just got approval for a new grant for next year. So we'll be passing that information on to you folks later on.
This is us, but you already saw we were introduced by Ed. Thank you for that, Ed. So the first topic that we were asked to cover was what are the differences, I guess, between hydromechanical and gravity grease interceptors. And I do an online course. I do an in-person live training course that are 6 modules long to explain all of this. So Clayton and I got together and we shortened all of this material up into what we hope will be just an hour, and God willing, we'll nail that. If you want to understand the difference between hydromechanical and gravity grease interceptors, I'll try to briefly describe this for you. So we have to go all the way back to World War II, because really it was when the United States was dragged into this war, and all of the consequences of being involved in the war, the shortages that happened, the needs for glycerin, certainly for a variety of different products that were used at the time. And one of the programs that came out of that war effort was the Fat Salvage Campaign, and the goal of that was to not only have mom at home save waste fats from her cooking processes, but also for the U.S. military to participate in that. And when the military did that, they looked at the landscape of available products, and there was no standardized testing and rating program for grease interceptors. So you had a variety of manufacturers who all made grease interceptors, but they all made them and rated them themselves. So today we would describe those as factory rated, meaning there's no harmony or synergy between those ratings. So the U.S. military decided that they wanted to take action about that. They went to the Iowa Institute of Hydraulic Research and asked those folks who they had a working relationship with on a variety of projects concurrent with their other projects related to hydraulics, I guess. And so they asked them to create a testing and rating protocol for commercial grease interceptors, or grease, in this case, grease interceptors for military installations. And what you're looking at here is an image of a drawing of the original grease interceptor testing apparatus, which just used a supply tank, a flow control valve that would be used to set the flow going into the interceptor, an on-off valve that you see here listed as a quick action valve, and then a mixing funnel. And during the test, someone would uniformly pour hot lard into this mixing funnel as the water was coming out of the supply tank into the grease interceptor, and whatever escaped the interceptor and went into the catch basin, they could take that catch basin, what went into the catch basin, skim that off, dewater it, and weigh it, and then compare that with what went into the interceptor. So then the question would be, how would we determine efficiencies? Well, in this case, they decided on an average efficiency of 90%. So if 10 pounds went into the grease interceptor and 1 pound escaped into the catch basin, then that would be 90%. And so they would test an interceptor then multiple times to determine its efficiency as an average, and then the minimum capacity for that device was decided to be 2 pounds of grease for each 1 gallon per minute of flow rate. So if it was tested at 20 gallons a minute, it would need to hold 40 pounds of grease. So this protocol became the required performance test for all military installations moving forward, and that went on for quite a long time. The Plumbing and Drainage Manufacturers Association took that same research. They were participants in the development of that, and went over to a separate testing laboratory and developed the first commercial standard called PDIG 101, and we'll touch on that in a bit. And they used the same criteria, which became part of the plumbing codes moving forward from there. And again, that was 1949. But up until the 1970s, there was no distinction between types of grease interceptors. They were all called grease interceptors. And so if you want to know, I talk about this in terms of the evolution of grease interceptors over time, and in terms of a distinction between what we call hydromechanical grease interceptors and gravity grease interceptors today. There wasn't any such a distinction prior to the 1970s. When you get to 1970, what happened in 1969 was the Cuyahoga River had caught on fire for the 13th time. And here we are as a country. We've landed on the moon. We just had, Woodstock, and all kinds of fun was going on. And we had this enlightening and an awakening in America. And a lot of people started wondering why we have rivers in America catching on fire. So President Nixon formed the Environmental Protection Agency and gave them an assignment, which was to report to Congress and basically, to simplify all of this for you, tell us why rivers are catching on fire in the United States. And so they did. They went to the Congress and they said, look, the reason we have rivers catching on fire is because we treat them like liquid garbage cans, and all industries just discharge without concern for what happens. And the Cuyahoga River and that stretch that was on fire was described by Kent State University as dead. It had no life in it whatsoever, and it had a oil slick that ran at least 3 miles down it from shore to shore. So truly it was a problem that needed to be addressed. And so Congress then addresses this by establishing the Clean Water Act, which basically just takes the Federal Water Pollution Control Act and modifies it, gives it some teeth, and then it funds construction of sewage treatment plants. One of the things that it did is it funded construction of treatment plants under the Construction Grants Program. Now, this is important in terms of the evolution and change of grease interceptors over time, because when you are, prior to this, most of the country was still governed by on-site wastewater treatment, known as septic systems. And so in the wake of this, we're now going to be building out publicly owned treatment works, which includes the collection systems, and we're going to have people abandon those on-site systems and start tying into these collection systems over time. So we have, in terms of the evolution, we'll pick up the story here in Los Angeles, where a manufacturer of said devices has this device going for him, and he basically says, look, I'm making residential septic tanks, which are not going to be residential septic tanks anymore. And so we're going to have to look at what we're going to do here in the future. And so they repurposed these tanks as commercial grease interceptors and developed a sizing methodology and so forth. This picture that you're looking at actually came out of the 1980 EPA's Guide to On-Site Wastewater Treatment and Disposal Systems. So this got promulgated not only to the EPA, but you'll see it also got promulgated to the Uniform Plumbing Code. One of the fundamentals that we need to understand about how all grease interceptors work, because up until now there was no distinction between types of devices, and many people today think that there is a distinction between these devices in performance. In other words, how they work. You'll hear words like, well, these devices work off of Stokes' law. I've heard people say, well, no, but these smaller devices work off of Bernoulli's principle. And the fact of the matter is that all grease interceptors work off of a simple principle called gravity differential separation. And really, I don't have time to go into all the ways in which gravity differential separation works. There are a number of factors that affect it. But what we do know about it is that if you want to control, if you want to create an effective device, then you need to distribute the flow in that device throughout the cross-sectional area. And that requires some form of mitigation of velocity, which is one of the major challenges for any device that will pass a performance test. We need to create an environment that allows it to perform well, perform effectively. And in order to do that, you've got to be able to distribute the flow, which means a form of controlling that flow inside of the device. And so when we look at gravity differential or gravity grease interceptors, here's just an example of an IATMO Z1000 standard type of a device. And what we're seeing here is that there's no control over the flow. So if we were to try to distinguish between hydromechanical, today it's called hydromechanical, but grease interceptors of two different types. When this interceptor was introduced in the 1970s, it became known as a gravity grease interceptor. Its performance has always been assumed because it's a larger tank. Its performance is assumed to work off of Stokes' law because grease is lighter than water, and because of that, it floats, it will rise to the surface and sit on top, assuming we have the correct environment. It's always been assumed that because residential septic tanks have a scum layer, residential septic tanks are really good at doing what they do. They're just wonderful solids separators. Of course, that's their primary job. That somehow the assumption is that they would work well as commercial grease interceptors, simply based on the assumption that their larger volume would make that happen. The problem that we've discovered over the years is that there's no mitigation of flow. And so we dump in a 4-inch pipe, we dump whatever that effluent is directly into the bottom of the tank. And of course, there's no mitigation of velocity. There's no directional flow characteristic to it. And so you end up with a very turbulent flow environment, especially at higher flow rates. And as those flow rates increase, performance dramatically decreases. And so we use these today under the assumption that they must be really good because you've got this big swimming pool outside, and how can that not be a great gravity grease interceptor? So what's different about this now is when this was introduced, then all of a sudden we took those smaller those performance tested devices, and we gave them a new name. We started calling them grease traps. And basically the industry said, those are what we have inside, and they're the single fixture, maybe 1 or 2 fixture application. But grease interceptors became the colloquial term for gravity grease interceptors, what we call them today. And really the chief difference between today's products, meaning gravity grease interceptors, and sort of this evolution is, today we've got this, it's a subcategory. I can only describe it as that. There's no such thing technically as a high capacity hydromechanical. There are hydromechanical grease interceptors, and they are performance tested devices. I distinguish between legacy hydromechanicals, which all meet the minimum requirements of performance of the standards. I distinguish between those and those in this newer category that I call high capacity, a subcategory of those that are maximizing the volume for grease storage in their tank and maximizing the efficiencies of the tanks themselves. That's these. I'm showing you 3 examples here: the Endura XL100, Shears Great Basin GB250, and Thermoco Trapzilla's 1826. They're all examples of high capacity hydromechanical grease interceptors. Clayton, any comments on that?
Nope, not right now.
So again, we're trying to cram a lot of content in here to a short period of time. And so in order to understand sort of, the next area of concern, which is how do we know gravity grease interceptors don't perform as well as hydromechanical grease interceptors? And that means we need to look at the product standards themselves for a brief period of time here. And so when we look at the various different standards that we have out there, we're looking here at PDIG 101. That's the oldest standard. I'll go through these in brief, the most important ones. PDIG 102, I won't go into any length of time on that because it matches a grease interceptor with a sensing or an alarm device. ASMEA 112.14.3 governs passive hydromechanical. 14.4 is automatic grease removal. 14.6 are fats, oils, and grease. These are disposal systems, on-site disposal systems of fog inside of a device. CSA B41 is the Canadian standard for hydromechanical grease interceptors and automatic grease removal devices. And then IATMO Z1001 governing prefabricated gravity grease interceptors. So I'll touch briefly first on the IATMO Z1001 box. For lack of a better term, this is a residential septic tank. Its design is based off of IATMO ANSI Z1000, which is the residential septic tank standard for prefabricated tanks. And as you'll note here, this is it really just has a prescriptive design. If I opened up that standard for you and walked you through the whole thing, you would simply see prescriptive design elements. And then when you walk yourself down to, okay, well, what are we testing it for? Well, structural load testing is required, cover load testings are required, and a leakage test is required that assures an owner that when you install this box in the ground that it won't leak. But that's the only test. There's no performance test in it. And so today, as it was first introduced from the very beginning, we have a box that everyone has accepted as being the correct solution for grease interceptors without any validation of performance. If we look at the difference between that and hydromechanical grease interceptors, you're going to notice that these devices have to be tested and rated for performance. When it comes to the difference between the standards themselves, let me just briefly touch on that. This is PDI G101, and you'll notice here that it requires an external vented flow control. And that's the primary feature that's required for that standard. There's another distinction, but that's really the big one because it doesn't allow for any other type of flow control configuration. And what's important about that, especially for any field inspectors, is if you're looking at a device that's tested that standard and you see the PDI G101 label, we really need to be looking to see whether or not that device has the flow control installed. And not only the flow control, but a vent. If you're, for example, we've got friends in Canada who have lots of PDI labels on grease interceptors, but there's no external flow control, or if there is, there's no vent. And it's some workarounds people are trying to do to get away with some challenges between the standards and the codes up there. So when you're looking at a hydromechanical interceptor with a PDI label, as an inspector, I want to make sure that the device is compliant, which means I want to make sure that that device is performing correctly. And the only way that it can perform correctly is if it has its flow control installed. So as a pre-treatment inspector, you certainly want to verify that. So in terms of performance with regard to this, I'm not opposed to external flow controls in any way, shape, or form. They actually have been proven to enhance efficiency and also mitigate the velocity entering the device, plus add some air entrainment. So they actually are an effective tool. Certainly would want to make sure that they were installed. In terms of testing, the apparatus looks different. Certainly today, this is not actually drawn to any specific code. It's just sort of a compliant drawing with what's within the performance test in the standard itself. And here, instead of a tank heated with steam, we use tankless water heaters. Instead of directly dumping from those tanks, we use sinks today, test sinks, and then we alternate, put lard in one sink, and then in the next test you put it in the other, and you just rotate back and forth. And it's designed to be a stress test. And so once again, you're going to introduce lard into one of these sinks, and then you're going to dump them together, and then whatever escapes the interceptor into the skim tank will be skimmed off, dewatered, and weighed and compared to what was introduced. Notice that the run time here is 2 minutes. Very important to understand these devices all perform at peak efficiency in just 2 minutes. So when it comes to the big debate about gravity interceptors being what's the most effective residence time, the fact of the matter is, with good flow and the correct environment, a 2-minute residence time is ample for performance. And then, of course, we're still using lard today. There's some people have lots of questions about whether that's the correct media. I can explain to you later that it is certainly the correct media. Now, when it comes to the actual certification, this is where we begin to see some interesting things that have happened over the years. Up until about 2012, there was only this certification. You must test your grease interceptor to the maximum grease capacity. Legacy grease interceptors were always tested to their maximum capacity. But the motivation from the very beginning was a military installation in which maintenance wasn't really a question. You're going to have some privates going to be told to clean out the grease interceptor, at least once a day, or maybe more than once a day, and it wouldn't really matter. It's a military installation. They can do it as often as they need to. It became a problem when you started to apply these things commercially, where we don't have military command structure, and so look, I raise teenagers, so if you've got a 16-year-old kid that you're telling, hey, go up, clean that out, he may or may not clean that grease interceptor out when you want and on the frequency that you want. So, you kind of have to micromanage that process, and that's probably not going to happen. And in fact, over the years, it didn't happen. So we end up with this history of these things being perceived now as too small. They don't have enough capacity. And it's simply a function of the fact that they were never designed from the beginning to have a large amount of grease storage capacity. You saw that they were only required to hold a minimum of 2 pounds for each 1 gallon per minute. Now, what's important about this is how to understand what this says about what performance should be, how performance should be decided. And notice that it says here that it shall be established at the increment preceding, which means one before, 2 successive increments in which either the average efficiency is less than 90%, or the incremental efficiency is less than 80%. If you've never looked at a test report, this can be confusing. So let's look at a test report. So here we're looking at a test report for a device tested at 75 gallons a minute. And here, this is the incremental portion of the test report. And so we look at this to evaluate a couple of things. When it comes to ratings, you have, first of all, you have a rating which was not previously allowed in this standard. Now this standard allows for not only a maximum grease capacity, but it allows for a rated grease capacity in which the device is allowed to be tested to just the 13th increment. And at that 13th increment, under this standard, PDIG 101, if it holds a minimum of 2¼ pounds of grease, so if you've got 75 GPM and you multiply that by 2.25, that means it needs to hold about 167 or 168 pounds. If it holds that and then the average efficiency is greater than 90%, you can stop the test there. And we have some manufacturers that have done that because it's much cheaper to stop. But let's look at what we're looking at if we do that and what the disadvantage to a rated capacity is versus maximum capacity. So if this manufacturer here would have stopped at the 13th increment, so here's an incremental run. This column here is your incremental data, and then this is your accumulated data. And under this, we're showing the amount added, the amount skimmed, the amount retained, and then the efficiency for that run. Under the accumulated, then it's the total amount added, the total amount skimmed, the total amount retained, and then the average efficiency of all of the increments combined. And so instead of 168 pounds or whatever it would have to be, here it shows 191 pounds, and the average efficiency is 98%. And so given that those exceed the minimum performance requirement, this device would satisfy a rated capacity. But if you look down here, this manufacturer chose to continue with testing all the way out to the 47th increment. And what we learn when we do that is at the 45th increment, well, notice here under the incremental, the requirement was under the incremental that it must be 2 successive increments below 80% or an average efficiency of below 90%. And here we notice our average efficiency is above that. On all of these, it's still above that. So we look at our incremental and we see here 2 successive increments below 80%. So we go to the increment above those two, and we see that the interceptor actually held 649 pounds of grease at an average efficiency of 96%, and that's what it would be certified to. Now, I'm going to let Clayton talk about this chart here.
We had an engineer that was working with Clean Water Services, and he took those charts of incremental test data, and he put a graph together, which was quite telling, because according to the graph, once you reach your maximum capacity, for all practical purposes, the grease is going in on one end and out the other of the grease interceptor. One of the reasons we did this is because historically, public utilities give food service establishments so many days to pump out an interceptor if it's full. One of the problems with that is if the interceptor is full, it is putting grease into the sewer line. So if you give a food service establishment 30 days to get their interceptor pumped, they're putting grease into your sewer line for 30 days without any kind of treatment. We call that catastrophic failure of the interceptor, because they'll hold grease until they're close to 90% full, and then the grease just goes through the interceptor. One of the items that our boss chose when he looked at this chart, he started wanting to gather information from all of the max capacity tested units that were going into our service area, because he wanted to try and figure out where the maintenance should be performed. Should be performed when it's 80% full. So those two red lines on the graph underneath the blue arrow was Bob's attempt to try and nail down a good performance position or a maintenance time for each one of the interceptors. So this is important information. I think it really helps to see a lot of legacy pretreatment programs have a 25% rule in their ordinance language that requires restaurants or food service establishments to service a grease interceptor when it has 25% solids and grease. And a lot of the high capacity units that are going in now that are maximum tested will hold a lot more than 25% before they're serviced. So it's something to keep in mind.
While we're talking about the 25% rule, look at this chart back here. All of the legacy style hydromechanicals, formerly called grease traps, it was James Baginski in Hawaii who actually first discovered a ratio when he was developing the 25% rule, and he's really the first proponent of this concept of a rule of thumb for gravity grease interceptor pump out scheduling. And it was, how do I know if a gravity grease interceptor is full? And he didn't have any way of knowing that because they're not performance tested, so you couldn't look at a test report and discover that. So what he did is he went to performance tested hydromechanicals, all of the legacies that were available, because there wasn't any high capacity type available in the late 1990s. They were all legacy style hydromechanical. And when he evaluated the amount of grease at the end of the performance testers at the breakdown point for those devices compared to their liquid capacity, he found that they all fell within a range of 25 to 35% of their total capacity at maximum, meaning they could hold a maximum of 25 to 35% of their grease capacity, of their total capacity in grease. Hope that makes sense. They could hold a maximum of 25 to 35% of their total capacity in grease. And he simply chose to use 25% as a conservative value for using that with gravity grease interceptors. And then he further made it conservative by saying he would add both solids and grease together to form that 25%. That's where that rule came from. But if you look here at this chart, what Clayton's saying is if you look at this chart, the modern high capacity hydromechanical is so far above that in grease retention that we don't want to apply the 25% to these devices. Now you know where it came from. It came from legacy hydromechanicals tested to the minimum. So we don't want to apply that to the newer high capacity types because they certainly are doing much better than the minimums.
We also don't have any test data from the gravity grease interceptors to know if it's accurate. We had we had an engineering firm come out and do tube testing on several gravity grease interceptors that were in our service area. This was about 8 years ago. And they found some interceptors that were bypassing grease at 13% capacity and some interceptors that were bypassing grease at 30%. So it's kind of by gosh and by golly on gravity grease interceptors. And we have yet to get gravity grease interceptor manufacturer to go through the testing protocol. So we've tried, hadn't happened yet, although they may be getting close.
So, and on that subject, before we move on to our final area here, which would be sizing and selection, and then we've got a couple of things to talk about, and then we want to answer any questions that you have. But when it comes to performance testing and gravity grease interceptors, the challenge has been when we've met with the big prefabricators like Oldcastle Precast and Jensen and so forth, Park, those guys could afford to do testing at a single facility and then create a design and use that throughout multiple facilities. But there are a lot of mom and pop prefabricators out there that make 30, 40, 50 grease interceptors in a year, and that's it, who could not possibly afford a $200,000 test of each size. And it could be that much if their design was efficient, which we know that they're not, so it probably wouldn't be quite that much. But you get the point, it's expensive. And the mom and pop shops can't afford to test 4, 5, 6 sizes of gravity grease interceptors to validate performance. And there isn't any universal design that we know is validated for performance, and all of them make it somewhat differently. There are small variations from different prefabricators. So it's a challenge, and we haven't found any universal acceptance of that. I will say that there are manufacturers who are certainly pursuing this, and without naming names, there are manufacturers who are interested in performance testing gravity grease interceptors to validate them. Because they see the wave of the future. The wave of the future is performance testing your device. That's what we want. That's what everybody should be asking for. It's what we have a right to have. And with these new high capacity hydromechanicals, there's no reason to settle on an untested device and just assume that it works. We don't have to do that anymore. We can have performance tested devices. Did you want to anything else?
No, well, the only other thing is, because of the feedback that municipalities have been giving some of these manufacturers, we have seen improvements in performance, even though we haven't tested them. We have seen some of the gravity grease interceptor manufacturers make some design changes, and they have improved the performance, and they've also improved the ability to do maintenance on them. So I will stress the importance of providing feedback to manufacturers if you have an opportunity to. We have seen the manufacturers respond to that feedback in a positive way.
Absolutely. All right, let's try to quickly go through sizing. This is challenging. Normally sizing, when it comes to sizing grease interceptors, this is done with a focus only on flow rate, and that flow rate is either used by itself, or it's used to figure a volume in liquid for gravity. So hydromechanical are always sized according to the flow rate entering the device. Gravity grease interceptors are sized according to the liquid volume associated with that flow rate to give a retention time. All of the modern sizing for gravity uses a 30-minute retention time, and of course hydromechanicals are just based on flow rate alone. And so if we recommend a two-step sizing methodology. I'll call it a methodology. Step one would be the technical basis for sizing any device, which means to manage whatever the incoming flow will be, and to have performance associated with that flow rate. And so this is pulled, I believe, out of the Uniform Plumbing Code, 2018 Uniform Plumbing Code, what you're looking at here. And so it offers either a pipe diameter or a fixture volume method for sizing grease interceptors. There's tons to go over here that I probably don't have enough time to go through. So let me just explain briefly what you're looking at here. On the pipe diameter, you have a maximum full pipe flow. So why that's there is because the sizing of the interceptors for 1 minute or 2 minute drainage period are based off of this maximum full pipe flow. And what you need to know about that is it simply takes the pipe, it slopes it down at 1/4 inch per foot, or 2%, and asks the question, if this is cast iron pipe, that's what the friction factor of N012 means, cast iron pipe, what's the maximum water that could flow through that pipe? And so that's what you're seeing here, 20 in a 2-inch, 60 gallons per minute in 3-inch, and so forth. When it comes to sizing the interceptors, this is a departure from what the code does with anything else, because the pipe is never sized based off of its maximum capacity. For example, when an engineer goes to Chapter 7 and says, what pipe diameter do I need for this, for this area of the building? It's going to add up all of the fixtures. It's going to use drainage fixture units to calculate the pipe diameter such that it would not drain at its peak drain. It would not exceed 50% of the maximum capacity of the pipe. So at the peak drainage period, it would not exceed 50%. And the reason for that is that gravity drainage systems require air to function properly. Without air, we get lots of water, hammer, and slugs going in there that are very damaging to the system. And so we want air in those systems for them to function properly. And that means that they're designed to be at peak flow rate to be not more than 50% full. We reserve 50% for air. That's what drainage fixture units are intended to do. The challenge with applying drainage fixture units to a kitchen, though, is you're going to have some sudden massive volumes that can come together in very high rates for very short periods of time. And so you have to make a decision about whether to use a 1 minute or a 2 minute drainage period. A 1 minute, as you now know, would suggest that this pipe is capable of delivering. Once you get outside the building, we're not going to see 1 minute volumes of water. You've got too many feet, what we call developed feet of pipe. There's too much of that, and so you don't see these kinds of flow rates outside the buildings. And if you look at the work report, they've analyzed flow rates coming out of buildings, and they never saw anything greater than about 45 gallons a minute. So we know developed feet of pipe absorbs a lot of liquid. So we would normally, outside the building, we would normally suggest use a 2 minute drainage period. When you're using so that's what this column over here is for. This is normally outside the building. When you're talking about fixture flow rates or fixture volume, this is the fixture volume method. And the fixture volume method would take the length, the width, and the depth, which in inches, and that would give you cubic inches. If you divide cubic inches by 231, you convert that to gallons. We use a 75% fill factor. You can imagine, fill the sink up to its brim and then dump a bunch of dishes in it, and what happens? And then again, a 1 minute or a 2 minute drainage period. And in this case, we would want to look at and see whether we have directly or indirectly connected fixtures. For most of this, I give some detailed explanations. I have an online guide for sizing grease interceptors on my website. You can go there and see it. It's a downloadable thing, and it would explain in a little more detail when to use a 1 minute or a 2 minute drainage period if you want to go into that. We're running out of time to be able to go into a lot of depth about that. So I'll just suffice it to say, when we're talking about indirectly connected fixtures, we want to use a 1 minute drainage period. When we're all directly connected, you can use a 2 minute. When you do this sizing correctly, this step will not be that relevant to you. I'll explain. Back in 2016, we approached the American Society of Plumbing Engineers, who have this set of design handbooks. So when a plumbing engineer graduates from college or university, he doesn't graduate with a plumbing engineering degree. So he has to learn how to apply his skills to plumbing components and equipment. And this series, developed by the American Society of Plumbing Engineers, provides 4 different books that teach everything an engineer would need to know, the fundamentals of what an engineer would need to know to design a plumbing system. One of those books is this handbook here on plumbing components and equipment. Chapter 8 of this governs grease interceptors. Max Weiss, who is the director of the Plumbing and Drainage Institute, and I combined to edit this for the 2016-2017 edition. And what we did was introduce, what I did, Max didn't necessarily agree with all that happened here, but what we did was we introduced something that hadn't been used before, and it's called grease production. Because grease interceptors are certified not only to a flow rate, but to a capacity. And those manufacturers that certify to a higher capacity can distinguish themselves with that capacity, and that has real value for an owner or an end user. So where it came from briefly was Clayton's group had basically hired Kennedy Jenks to conduct a brown grease feasibility supply study, and within that study they were able to take a whole bunch of different types of menus and restaurants and so forth, and come up with some categories called low, medium, high, and very high grease producers. And then using, I think it was volatile solids, they were able to come up with some estimates on performance in terms of production of grease in volatile solids for different menu types. And then we took that information, we went back to those same FSEs, and then we calculated average meals served per day for each one so that we could apply a value to each type of those menus. And then we broke them up in the same manner in which not only Kennedy Jenks, but also Clean Water Services broke those up. So that's their contribution to that. And so you have here low, medium, high, and very high grease producers. And for those of us who've been doing this for a while, these are all 4 very legitimate categories. There are definitely applications for different menu types for each one of those. But I will say this, to just apply this like this has been somewhat challenging in the industry, especially for jurisdictions who want a clean and simple partnership with their businesses. A lot of end users will simply say, I don't produce any grease. And so it's always challenging when you go to them with this chart, because for some reason they seem to think of this as a measurement of how evil they are or how rotten they are as a human being, when that's really not what that's about. So what we did then is we simplified this, and we went to this table here now. So this is 30 different menu types, as you can see, 30 different menu types. And then without fryer, without flatware. So that's our lowest category. Without fryer, but with flatware is a little bit more, our higher production. With fryer, without flatware is higher still. And then of course, with fryer, with flatware. And what the flatware portion means is, if they're using disposable, then a fair amount of grease leaves and is thrown away elsewhere. But if they have their own flatware, then that's going to be dealt with on site. So you're going to be taking some of your grease back. So that's what this is about. So that table is just a number of factors. There's no evil in this. You're not a bad guy if it's just a factor. And so we found a lot more acceptance. And this has now been codified in 5 or 6 different FOG programs that I have personally written or amended for pretreatment programs across the country. We've codified this, 6, 7 times at least that I can think of. So it's becoming quite popular. But how does it work? We take the grease factor from that table, I pulled this out of the one that is online, and online it's table 2 for me, so that's where table 2 comes from. We take this grease factor from table 2 and we multiply that, oops, over here, we multiply that times the number of customers or meals per day, and then what is the time between pump outs that we're looking for. That will tell us the grease capacity required in the device. Okay, so if I take a simple example here, we only have time for one, so I'll walk you through. This is a real example where it's an Italian restaurant. You'll notice here it's Italian with fryer with flatware, and it has a 4-inch drainage pipe, which was, in this case, this is an outdoor installation. But in terms of how we would size it, we look at a 4-inch pipe, 1 minute drainage period would be 125 gallons a minute, but we know outside we're not going to see that kind of volume, so we would use a 2-minute drainage period for the minimum flow rate, and that would mean for step 1 a minimum of 75 gallons per minute. Maximum. That would be the maximum required. Yes, correct. Now, so if we look at the menu itself, that's Italian with fryer with flatware, so that's going to be column D. So 22D is 0.0455 pounds per meal, and as you saw previously, 469 meals were the average meals per day. So when we combine this information, 0.0455 pounds per meal, 469 meals per day, that's 21.3 pounds of grease per day. Would love to walk you through all the legacy installations where we've got a 40-pound trap serving that's being pumped out once a month, and it's full in 2 days. And we wonder why there's a problem with grease in the system. People don't understand how much grease is actually being produced. And when you see these numbers, it's eye-opening. So we're producing 639 pounds of grease per month. If you can imagine 40 pounds being captured, we're basically discharging 95% of the grease to the system, because it's not going to stay in the grease interceptor if it's a legacy style. So if we know this information, now can we size this interceptor more effectively? The answer should be yes. Let's take a look at some options here. Here we have, if we just used 75 gallons a minute, we have some options. Here's some legacy styles, a J.R. Smith or a Josem. Wade and Watts don't make 75 GPM units. Zurn does in this size range. 150 pounds of capacity, which you'll notice gives us 7 days. So once a week in this size range, once a week. And if I think I used for this, I used $100 a pump out. So if somebody was to actually pump this thing out correctly, they would be spending about $7,500 a year, $7,600 a year to correctly maintain this. It's one of the reasons why people will choose enforcement against pumping out, because it's normally cheaper than that. And so we have to be aware that if we want to entice people to compliance, one of the ways we can entice them is by reducing the cost of compliance. And here's the way you do that. So let's drop down to some larger, to some of these high capacity types, which is, well, this GB3 is not, as you can see, 175 pounds. This Endura XL 75 at 559 pounds would give us 26 days at just $2,000 a year. The Shear GB75, 31 days at 1,761. Trapzilla's TZ1600 at 30. If I walked you through all the problems at this facility, it would just be to illustrate that we have no control over bad behavior. So we want a margin of error in sizing any grease interceptor. I would definitely want to consider what's the next size up from this for grease capacity. 26 days. If they're really bad behavior, I have to get them down into something that's less than once a month, or more often, excuse me, than once a month. And most people will not do it more than once a month. And I guarantee you, in a room of 20 people, 18 people will raise their hand if I say, would you be happy with once a month? Because so few will actually even do that. So let's step up to 100 gallons a minute and see what our options are at this. And this is where the bulk of the high capacity market has transferred to, meaning pump out frequency here at the legacy 100s would be at 200 pounds, right? 2 times 100 times 2 is 200 pounds of capacity. Still 9 days, they're not going to do that. But what about here, what we're seeing here now? So here's this Endura XL 100, 1,058 pounds. That gives us 50 days at $1,400. Shear's new GB250, so they've retested this with a new inlet configuration, and it now holds 1,751 pounds, which would give us 82 days. Trapzilla's 1826 would give us 86 days. So look at this. I mean, for $875 a year, $800 a year, it's like 75 bucks a month. That's affordable. that is affordable to a restaurant. That's affordable compliance. And now if we looked at what they could do here with these newer models, the GB500, the GB1000, these are the high capacity, these were designed to be gravity grease interceptors originally, and they're now performance tested gravity at 500 gallons and 1,000 gallons. And notice 3,000 pounds of capacity, 6,500 pounds of capacity. Would we want to let a grease interceptor go 143 days? No, not in any way, shape, or form. 300 days, almost a year? No, the biology would kill us. And you have to look at this, multiply it times all the FSCs before you make that decision. Would we want everyone doing that? In order to make this work, we have to make sure that all the fixtures are connected. And we are running out of time here, so we want to make sure that we just illustrate. You or I, not one of us has any control over what happens in a kitchen. And every fixture in a kitchen is impacted by fog. And that's why we try to illustrate this. The left side illustrates, hey, this is the promise of clean and pristine fixtures when they're first installed. But the reality is, we don't have any idea how they're going to use those things, and they normally use them wrongly when it comes to fog impact. And I want to let Clayton explain this next thing for you here. This is a case study where we had 4 different facilities that had the old legacy systems installed, and we tracked the grease production by pump out of each one of those facilities. We had them do retrofits where they connected all fixtures and drains to a high capacity grease interceptor, and then we measured the grease that was captured. So each one of these typically had the 3 compartment sink hooked up to a legacy under the sink trap. When they were reconfigured, all fixtures and drains in the kitchen and food service area and food prep area were connected to the grease interceptor. Typically, we saw a factor of 10 times more grease captured, with the exception of the hospital. The reason we didn't see grease downstream from this hospital, which is one of the largest ones in the Tri-County area here in the Portland metro area, is that hospital discharged into a major trunk line. And so there was a lot of flow, a lot of turbidity, and the grease didn't have a chance to collect inside of the trunk line. We did see grease at the treatment plant. But this is a pretty good illustration of the difference between having a restaurant that's designed under an old code here in Oregon since 2013. Any food service establishment has to hook all fixtures and drains in the kitchen and food service area up to an interceptor. The only exception is the bathrooms, the sanitary drains, and there are a couple of other exceptions for condensate drains. But if there's a floor sink or a floor drain in the food service area and an ice machine goes into it, that drain will be connected to the interceptor. So this is a graphic illustration of the difference between the old design and the current plumbing code here in Oregon and the capture rate for grease. So it does 2 things, though. One, it illustrates that the effect of having all fixtures routed to an interceptor, and number 2, having a high capacity device that captures all of that grease. Mm-hmm. So it's really a twofold strategy that makes it much more effective. So let's talk briefly now as we wrap up here of some of other resources that you have, places you can go to get help or more information, which is certainly important for you, because again, we've tried to cover a lot of information over a very short period of time. Normally, Clayton and I give independent classes from each other that are both a full day that provides contents that mixes this level of detail only far greater. One of the resources you have is newly developed is the Fog Training Institute. You can just go online to fogtraininginstitute.com. And this is a home that we've developed that is going to be the online education resource for fog program professionals. So if you need help in fog program or device management, we're building content on this site that gives you the ability to get this online, as opposed to trying to find some live presentation or some workshop you could attend that would give you content that's relevant. And if you've been to those, you know that you get a little bit of information that you walk away with, but it's hard to walk away with a whole lot of information that's useful. And if you've ever been to one of those that you thought you got a lot of that, you forget most of it right away because there's not much given to you to take home. So we wanted to create this resource for you that's an online training resource for you. And the featured course right now is my Grease Interceptor training course. 2019 edition, and I'll be updating that as things change. For example, codes are going to be changing in 2021, so this will be good through 2020, but we'll need to update that for the code changes that happen for the 2021 code cycle. Also, I'll keep up with that content, but we've got other content that's coming. We're going to build out some content that relates directly to FOG program development, the issues associated with that, and so forth. This is for Clinton.
Western States Alliance and Swift Comply, a company out of Ireland, have teamed up to provide a web-based FOG data management system. It's a subscription-based system where a city pays a subscription rate based on the number of food service facilities they have. I put their website on here because we don't have time to explain all of it, but it's a fascinating piece of software. The city of Gresham is using it right now. The city of Bend is getting ready to launch it. It's up in multiple cities across the United States. It's used all the way across the Republic of Ireland. So it's very effective, and it provides a single location for your pumpers. If you're in a municipal area that has a lot of different jurisdictions, like Clean Water Services, where we had 12 member cities that all wanted to use their own system, it provides a single system for all of the cities to use, and all of the pumpers have the same system to enter data into. So just be aware of that. Also, Western States Alliance and the Pacific Northwest Source Control Training Association provide two different workshops. The pre-treatment workshop is September 9th, 10th, and half of the 11th. That's in Vancouver, Washington. We also have an annual FOG forum that happens in Hood River, Oregon, April of 2020. We don't have the dates set up yet, but it's a 2-day workshop for FOG folks. We are also teaming up with other jurisdictions across the United States. So Southeast FOG Alliance, AZ FOG, we cross pollinate, I guess is the best way to say it, with speakers and topics with those other organizations.
Okay, I think that's that. So I'll turn this back over to Ed to moderate the questions.
Yeah, we got one question. What types of grease do you often find in the interceptor, and what can it be used for?
So am I still on?
Yes, you're still on.
Okay, this is Clayton. What kind of grease you find in a grease interceptor depends a lot on the type of restaurant that you have feeding it. So if you have a coffee shop, a lot of the material in the grease interceptor basically looks like chocolate pudding. There's a lot of oils in coffee and the creams that they use, the cream and milk products. The kind of grease you find in an interceptor, like with Asian food, like P.F. Chang's, tends to be, you find a lot of oils in the grease interceptor. Same thing with Mediterranean restaurants like the Olive Garden. You find a lot of olive oil in the grease interceptor. A lot of your American restaurants, steak and potatoes, let's see, Australian barbecue places, your burger joints, you tend to find grease, burger grease, in the interceptor. You also find food products. What's the grease used for? Grease recovered out of a grease interceptor has one of the highest BTU values for an anaerobic digester of any kind of waste product. So it's higher than creamery waste, it's higher than green chop waste, salad waste. So it's a huge gas generator for anaerobic digesters. A lot of the grease pumpers in the Portland metro area take their grease waste to either City of Gresham, which has a grease receiving facility at their wastewater plant, or Clean Water Services at the Durham facility in Tigard. There's also an anaerobic a farm digester down in Tillamook County that is begging for grease because they put creamery waste and cow manure into their digester, and the grease helps that stuff break down and generate methane gas. So hopefully that helps answer that question.
Yeah. Here's the next question for either of you. In the states of Oregon or Washington, where do pumpers deposit their grease? And are there any regulations that govern, give me a second, their disposal?
This is Clayton again. In Oregon and Washington both have grease receiving facilities at anaerobic digesters. I don't know where all of them are in Washington State. There are not very many of them in Oregon. Several of the grease pumpers take their grease waste to rendering plants. Darling International and Baker Commodities both have rendering services. They also operate grease pumping services as a sideline for their rendering facilities. And those two plants are able to separate the grease from the water and discharge the cleaned water under an industrial discharge permit to the cities, wherever they happen to be located. And then they do whatever they do with rendered grease, just like they do with the dead animals that they pick up. There is no regulatory tracking like there is with septage waste in the state of Oregon or in the state of Washington. I don't think there is in Idaho either. So that's one of the things, one of the tasks that we hope to be working on through Western States Alliance here in the Pacific Northwest, is working with the states to try and develop some kind of a tracking mechanism. And we're working too with Swift Comply to do in disposal or close the loop on where material goes. So that's something that's in the works. It hasn't happened yet. And right now, the state of Oregon, the folks that manage the septic plans in the state of Oregon don't really want to have anything to do with it because they're understaffed and underpaid.
Okay, those are all the questions that I have. If just as a reminder that we're going to be having this recording available on our YouTube webpage, I guess in the next 2 weeks or so, and we will be sending out a notification to all of you, letting you know with a link how to access it. With that, I want to thank Ken Laux and Clayton Brown for their excellent presentation. And with that, I'm going to go ahead and conclude this webinar. Everyone have a great day and eventually a great weekend. Goodbye.